Welcome to Calculus 1 lecture on limits. So let's first say right out of the box that the limits are a fancy way to compute function values. So we are looking for those y's provided x's. So this is unofficial, obviously, definition of the limit and what it does. Limit is a fancy way of computing function values. Now, I should actually replace the word fancy with powerful, word powerful, but I'm not going to because fancy is a fancy word. Now, why is it fancy? Why is it different? Let's immediately clear that up. Y equals f of x is from your pre-calculus course where we define the function. We know that input is x, the output is y, and let's say the example of this is y equals to x plus 5. So now you have a function. Function is x plus 5. We know we can graph this and we can get linear line going through 5. Since the slope is 1, it's going to be a 45-degree angle. Slope is 1, so 45-degree angle, and 5 is the y-intercept. So now we go and compute function values. So if f of x is equal to x plus 5, then f of 3 is how much? Is 3 plus 5, which is 8. And we can find that on a graph by going to 3, following up, and we see that that point is at the elevation 8. So this is from your pre-calculus course, where you learned about functions. I'm going to claim that the limit of x going to 3 of x plus 5 is also 8. And this is what we are learning today. Trying to understand what are the similarities and what are the differences between two methods, and trying to also understand why do we actually need limits. If the function values are computed just fine using the pre-calculus methods we learned a year ago, why would we have anything extra to add to it? So let's take a look at some situations. Let's say that you have a function that looks like this. Y equals 1 over x. You know this function, right? What is this function? It's a radical function that has the vertical asymptote at 0. And let's say that I ask you for f of x equals 1 over x to compute f of 0. What would you have to do? You would plug it in and you will be undefined. Very good. So you were not able to compute because we are not allowed to divide by 0. Then we're going to jump into another case, y equals x squared, whose graph looks very similar to 1 over x, except it has both of these looking up. So for f of x is equal to 1 over x, how much is f of 0 now? Still undefined. Very good. Now see, the trick is that if you use pre-calculus to compute these function values by plugging in 0, you are going to get undefined both times. However, if you use limits, one of them will be undefined and the other one will have positive infinity as the answer. So choosing to use a limit as a computational method will yield a different answer, which is actually more detailed than just saying undefined, which means does not exist. So we would like to understand what these limits do and how they do it so that we can figure out things. So let's go and start by understanding first how the limits compute values. The limit is never going to plug in the value that you are looking at. The limits are going to compute all of the values around the point that you were looking at. So let's say that you want to compute, we're going to go back to our original problem. So we have that our f of x is equal to x plus 5. And then we're going to have on the other side a limit of x plus 5. I would like to compute this at 3. So we said 3 plus 5 is equal to 8. On the other side, I'm going to say limit x goes to 3 is, limit of x plus 5 as x goes to 3 is 8. And now we're going to have a completely two different mechanics here. On the left, I already had this earlier. 1, 2, 3, 4, 5. We had that 45-degree line, and at 3, we got our 8 as the result. But the limit doesn't operate that way. The limit is going to do something completely different. So we still have the same function, same line as before. The limit is going to say, let me compute all of the values coming up to the 3, which means that we will be computing all of the values coming up to this point, which means we'll be getting all of the answers coming up to this point. This is what is known as the approach from the left. Now I can come up with a chart of values to do that. So in the chart, I would like to know what is the value as x approaches 3. So on the left, I'm going to come up with, let's say, 3 numbers that are smaller than 3, but they are building up to the 3. So let's go with 2.9, 2.99, and 2.999. So these numbers are getting closer, right? Think of it as money, $3. So you have $2.90, $2.99, and then when you go to pay for a gas, you have $2.99 and 9/10 of a, all right? You saw that 9/10 on the gas station? Next time you're there, ask for change. All right? Because they keep that every time, right? Over 100,000 transactions, it adds up just like in the movie, right? Which movie am I talking about? Office Space, very good. Do you have my stapler? No, okay. So let's compute these values. So now the formula is x plus 5. Remember, I am not allowed to compute at 3. I am allowed to compute at wherever the hell I want to around 3, but not at 3. So I will be computing at these numbers leading up to 3. So 2.9 plus 5 is 7.9. And then 7.99 and 7.999. You see how we are going to 8. Are we green on that one? All right, now for the blue approach. By the way, these approaches I call Romeo and Juliet because it's red and the blue. So we have the, probably it's too old reference because that story is really old. But apparently there used to be like 2 people and they fell in love and they died. That's a short story and a spoiler. Oh, I didn't say a spoiler there. But yeah. All right. So there we go. That's the approach from the other side. We will call this one approach from the right. which means that down the line will be going this way, and it will be going down the y-axis as our calculation goes. Now let's take a look at numbers. The number that it's far away would be $3.10, and then maybe $3.01, and then just $3.01 of a cent. And if we are to add 5 to each one of these, because remember, we are computing this in the function, so we have the function over here, x plus 5. We are computing all of these values around number 3 in that formula. We are not allowed to use 3. We can use anything else but 3. So we come up with numbers leading up to it from one way, leading up to it from the other way, and we go and we compute in that formula. It's a very tedious procedure. So we get 8.001, 8.01, and 8.1. So you see that both of these approaches are screaming that the actual answer is 8. This way is going to the 8, and this way it's falling down into the 8, which means that our answer should be an 8. It is crucial to understand, guys, that you never use 3 to compute anything. Now, I understand that when you start doing these problems later on exams and homework and so on, yes, you will take and say, oh yeah, x plus 5, 3 plus 5 is 8. Good, right? But this is the actual work in the background. Because, and next example will explain it why you're not using 3. Because there will be no need for any of this stuff if it was the same. You just plug in 3 and you have 8. Well, that's what you did here, right? This needs to be better. It needs to be special, okay? So treat it that way. And I understand that you will plug in 3 and get 8 and claim that it's an answer. But this is what it happens in the background graphically and through the chart. So that's what we are learning. These two approaches, which I call Romeo and Juliet for the reason, is the key aspect, because that will give us the major theorem which tells us whether the limit answer exists or not. If the two fall into the same number, the answer is that number. If they fall into different numbers, then the limit does not exist, i.e. the answer to the function at that point does not exist. So we're going to clearly define that now. But before we do that, let's take a look at one more example and try to understand the story here. So let's take a look at step function. F of x equals 2. We'll just take a two-piece step function. So let's go with x minus 1 for all x's from negative infinity less than x less than, I don't know, 2. Let's go with 0 because it's going to be cheap to graph. And then let's go with the x squared plus 1 for 0 to infinity. So now we graph this. It shouldn't be a problem to graph this at all because you know how to graph linear, you know how to graph quadratic. Just use the appropriate pieces. We're going to again use the y equal f of x, which is the pre-calculus part. And we are going to compute this at 0. So how much is f of 0? And we are going to also find the limit as x goes to 0 of our f of x. Now we are going to do this graphically, and then we're going to use the chart. So we get to draw the same graph again because it's the same function all the time. We have x minus 1, so minus 1 is the y-intercept, And we actually have to put the open circle there, because that is not included. If you take a look at the domain, you get to draw x minus 1 on the left side of the y-axis. So the highest x value that you are allowed to use is 0, which is there. So there will be no linear line to the right of y-axis. This is the x-intercept, and we have the slope 1 again, so it's going to be a 45-degree line falling down. 45-degree line to the left. And again, it is the open circle because there is no equal here. This one will get a filled-in circle at 0 because the equal is there. Now, can we put both of these to be filled circles? Why not? It wouldn't be a function. Very good. 0, in that case, would have two different values. So x squared plus 1 is the x squared function, which is a quadratic polynomial U-shape, right? It just goes up. So as you can see, it's fairly easy to graph these piecewise functions. Just graph the basic functions that you know from that list within the domains where they're supposed to be. That's why it's called piecewise. Piece number 1, piece number 2, piece number 3, right? As many pieces as there are. So that's the graph, right? And now you ask yourself, what is the f of 0? F of 0 is equal to 1. Very good, because that's what the field circle is. Very good, so it's 1. Awesome. Now we're going to unleash calculus upon this, and we're going to take a look at the limit of the same function and see what we get. So we have x, and we have y, and we have our quadratic piece going up, and we have our linear piece going down. So identical function as before. Now, as you get the red approach from the left going to 0, you see that the value is going down the line, and we are approaching the open circle, which is -1. If you look at the blue approach from the right, we are going down this line, approaching into this value, which is a +1. And now we are running into an issue where they're not the same. So, what's the verdict? Does not exist. D&E does not exist. So the limit does not exist. The limit does not exist. So functional value is 1, but the limit doesn't exist.
Where did you get 1? From the equation?
Well, you can look either where the circle is, but the idea is that 0 in a domain belongs to the bottom one. So plug 0, 0 squared is 0, plus 1 is 1. So we compute at 0, but on the appropriate line. Cool. So now we found that pre-calculus will give us the answer where the calculus limit will not give us an answer. It will say that it does not exist. And you might say, well, wait, that's restrictive because isn't it supposed to be more powerful? It is more powerful because calculus computed infinitely many points around. This one computed a single point, right? So the actual calculus, and we're going to get to this tomorrow and talk about continuity. If you are using only pre-calculus, right, and you are skiing down the slope, there's a cliff there, right? Pre-calculus does not detect that, right? Where calculus says, just don't, all right? So yeah, it is more powerful. So that's another example. So I hope that these two examples you were able to see. Oh, actually, wait, we didn't do the chart. We didn't do the chart. Let's do the chart. Sorry. Here be the chart. 0. let's find two values that are leading up to 0. Sorry, 3 values, and 3 values after 0, again leading up to 0. So we have negative 10 cents, negative 1 cent, and negative 1/10 of a cent. Oops. Positive 1/10 of a cent, positive 1 cent, and 10 cents. Cool. Now we get to compute these values in the piecewise function. Negative 0.1. Negative 0.1 belongs here because it's between negative infinity and 0. It's a negative number. Thus, we get to use this one to compute the value. So negative 0.1 minus 1 is what? Very good. Yeah. So you can see that the red trend over here is going towards negative 1 because negative $1.10 goes down into negative $1.01, goes down into negative $1 and 1/10 of a cent, and so on. So you see that the left approach goes there. Now, right approach is going to be more annoying to compute because of the x squared, but we can still do it. So we have 0.1 over here, 0.01 squared, sorry, 2 zeros, 1 squared is equal to what? Well, the fastest way to do this is to say that this is 10 to the minus 3. Are we agreeing on this? And then we square that, which is 10 to the minus 6. So, how much is this? This is going to be 1.5 zeros and then 1 at the end. We do the same for all others. Obviously, you can use calculator, but I am much cooler than that, so. Fine. Yes?
Isn't the easiest way to do this just to kind of like look at the graph and see that the number is so close to 0? You know what I mean?
Yes. And you hopefully will be looking at the graph most of the time. We just need to kind of give a little bit of this, comforting confirmation that the numbers actually follow and do what they're supposed to do. But you are 100% right. You should be looking at the graph and just making that conclusion. And the one at the end is going to be 1.01. So the blue approach is going into positive 1, and we get that does not exist, so D and E, because negative 1 and positive 1 are not the same. So this leads into that major theorem which I talked about existence of limits. And we are going to first define a few things, and then we're going to state that definition and theorem, and that will be the introduction. So let's first say that limit of f of x as x approaches a minus is a notation for left approach. And then just do the same thing for put a plus. Gonna check. So a plus is a notation for the right approach. Or well, let's put approach from the right. And approach from the left. In my notations, I used the left arrow, which was red, and over here, blue, which was approach from the right. Now, overall limit f of x as x approaches a combines the two from above. So every time when you just see a limit, you have to make sure that both sides are there. And that leads into a major theorem on limits. And here it is. If limit from approaching from the left, so x approaches a minus of f of x, is some finite value L, and that is the same as the limit approaching from the right, then we say that the limit x approaches a of f of x has the finite value L. The way to read this definition, memorize this definition, theorem, and understand this theorem is simply to say, if the limits agree from left and right, the overall limit is whatever they agreed upon. If the limits are different from left and right, have different values, then they have different value. Then the limit doesn't exist because they have different values. And now we can take a look. To understand this definition, we can take a look at two limits. This theorem, I keep saying definition, theorem. To understand this theorem a little bit better, let's take a look at the limit of 1 over x as x goes to 0. And in the blue corner, we're going to have limit x goes to 0 again of 1 over x squared, which is what I talked about earlier. Here are our graphs, so we don't have to compute 5,000 numbers. The left approach is going to go to negative infinity. The right approach is going to go towards the positive infinity. So what do we know? Does not exist, right? Why? Because the left limit and the right limit do not agree. On the other one, the limit from the left goes towards the positive infinity. The limit from the right goes to positive infinity. Therefore, the limit is positive infinity. Pre-calculus will, in both of these cases, give us does not exist. If you plug in 0 into any of these problems, you get that the functional value does not exist. Now, what are the limits also cool for? Well, since we never use the point that we are approaching in our calculations, the coolest thing is that that point actually doesn't even have to exist in a function. We can have a hole in the graph, and the limit would still exist, kind of magically telling us that if that value was there, its value would be, and then whatever number. Let's take a look at this. So let's say you have a function of some sort, and then there is a value missing at, this is 3, right? At 3. I don't know what this function is. It's completely irrelevant what the function is. The precalc, I told you I spell it with K. So the precalc would say that f at 3 does not exist, because there is no y value associated with that point, because the point does not exist. It's the open circle there. Where the calculus would say limit of f of x as x goes to 3 is 2. It exists, because the left limit goes into the point, goes up to 2, and then the right one from the right goes this way, goes down, also at 2, and we get the 2. I kind of don't like that that the function ended up going through 2 there. So let's fix that so there's no confusion later. There we go. So this is it. So even if the function value does not exist at that point, limit will still detect what the y value would be if that point was to be there. Obviously, you look at the graph and you know what the value is. Now, something like this will be popping up in tomorrow when we do more of this stuff. So let's have one of the annoying exercises. That will use the technology. I'm not sure if Mathematica is installed on the computers that you have in your desk, because we are in a process of changing computers. Over the summer, there's a lot of work being done in terms of upgrading and changing stuff, so on. So I'm not sure if you guys have, if anyone can quickly just go and look if there is Mathematica already in there. Let's take a look at this example. This is problem 18 from the textbook. So g of x is given as 3 sine x minus 2 cosine x plus 2 over x. And they're asking you to figure out the limit of g of x as x goes to 0. Now, I have to warn you immediately about plugging in 0 here. As soon as you see this x in the denominator, you see that that is not the way to do it. So, two options here. Graph this monstrosity, which means you have some kind of graphing utility to work with, Mathematica or your graphing calculator. But you have cell phones, guys. Just get the app that graphs on your cell phone. You can also get Mathematica for yourself, the Wolfram Alpha for the cell phone. I believe it's going to cost like $5 one-time fee. Where the one on a PC, if you go to the website, I think it's like $3 a month. So the cell phone version is it's very cheap, which you can use for graphing again. But there are, I think it's called a function generator light or something. There are free apps for graphing. Just type in graphing functions or something in the App Store, and you should run into few of those free things to use. Otherwise, I mean, you need to have something to graph this thing, and then just take a look what happens. 0. You can look at it. We're just gonna wait. If you have the memory. Also, you should connect your cell phone to our Wi-Fi. Not use your data. Yeah, well, please wrap it up. Whatever app you figure out, or if you have one of these EI80 somethings, you can use that as well.
How do you get onto the Wi-Fi?
I just use the key number, then can target that whatever. Yeah. Make sure you type everything in correctly. You're using Citrix. It's installed under Spark. I don't think it was Citrix. But it will work, right? Now, as you're graphing this, you're using Lambda calculator. Make sure you calculate with the gradients, otherwise you're going to get a whole bunch of stuff that doesn't work. What do you got?
It looks like the limits of these three.
Looks like the limit. All right. So let's. So you have the graph for this thing, and you can also compute the values, right? You can compute the values, come up with a chart, and then see the left and the right approach. All right, so let's take a look at the graph. We're going to use Mathematica. So if you go with the Wolfram Alpha query, you can just talk to it, right? So graph, and then you will just type in open parenthesis 3 sine x minus 2 cosine x plus 2 close parenthesis divided by x, and then hit enter. That's all it is. So you get the answer, and you can try oh, okay. Here's a clip file. And the clipping doesn't work with the best from Wolfram. I'll have to fix that. Anyway, I'll do the quick sketch. So what do we have? I have -2, 3, and what else? And then after the 4 somewhere. And it goes something like this. So the graph solution says that the limit of g of x as x goes to 0 is 3. And now we're going to do the chart. So we have a 0, and we're going to have -0.1, -0.01, -0.001, 0.001, 0.001, 0.01, and 0.1. So these are the values. And you use the calculator to quickly compute this. Make sure that your calculator is in radians, which mine was not. Okay, so 3 sine x minus 2 cosine x plus 2 bars y bars function 1. So let's see. I have 2.895 2.98995 and 2.9 2.998995. So clearly we're going into 3. From the other end, we have 3.000995. $3.00995, so 1 0 less. And when we compute the last one, we get 3.095 if you. So we've constantly lost one of the zeros approaching from the right. And you can see that the ones on the left are building up into 3. The ones from the right are going down into 3. So table or chart, whatever, it gives us also that the limit g of x is equal to 3. Now see, this is actually the way that you can use to solve any limit under the sun, right? These chart and the graph things. But maybe for some of these we can do a little bit better, so we're going to learn more techniques now in 2.3. Yes? I'm plugging these values that I picked. These are all x values. X, x, x. Yeah, except I use the feature of the calculator that computes the values quickly rather than typing it every time. Well, on TI-83, I'm using the vars button. Vars stands for variables, I guess. I use the vars feature of the calculator, but you can type in only once this, and then you can go second enter. It will repeat the whole thing and you just keep changing numbers. On different calculators, it's going to be on a different way to do it. Yes.
Oh, was something I know from for that the table feature ability and stuff like that.
Oh yeah, you can do the table feature too. Exactly. You can do the table feature and you can just set the start at the value you want. Because the increments are going to be 10 times every time, so it's not going to be fun to scroll like 400 numbers, right? If you put the small, so you will have to restart the table feature every time. But that's still fast. Good. If anyone is interested in how to use the vars, I can show you. But again, it's not something that you can use on a test, so why waste time? All right, so this is the introduction to limits. Hopefully you understand what the limits are, how they compute the function value, why and how are they different than computing function values using pre-calculus. Remember I said that the pre-calculus you actually plug the number and compute. And I hope you guys see that in this case pre-calculus fails, right? Because if you plug 0 here, you get 0 for the first term because sine of 0 is 0, so that dies. And over here you have cosine of 0, which is 1, so negative 2 plus 2 is 0, you get 0 divided by 0. And you ask yourself, how the hell is that equal to 3? You see it on the graph, it's equal to 3. You see it over here, it's equal to 3. But on the graph, if you zoom on this value, you will see as you open circle there. All right? And we are going to talk about that in greater depth tomorrow. So now we're going to hit the break. After the break, we're going to talk about algebraic methods to solve these. So other than the graph and the chart. Anytime you should use the graph. That should be your go-to method. But if that fails and if it's too complicated to graph and you have no graphing calculator and you don't want to go through computing the points, algebraic methods might be helpful. So I'll see you all in about 5 minutes. I'll restart the stream so we have a new title.